Today we will talk about the Huffman coding algorithm in the data structure. Suppose there's a very long string consisting of English letters from A to F with a total of 100,000 characters. The computer needs to save and transmit in binary. So what kind of encoding is the most economical? For example, the simplest and most direct way is to encode 000, 001, 010, 011, 100, and 101 from A to F respectively. Then the length of each character encoding is 3, and then multiplied by 100,000, which is 3 million. Number of 1 or 0. Is there a way to make them shorter? The answer is yes. In fact, the encoding method just now is called fixed length encoding. That is, the number corresponding to each letter is the same length. Is this reasonable? Is there a variable length encoding? Now we count the number of occurrences of each character. We will find that the number of occurrences of A is the most, and F is the least. Therefore, it seems that it would be better to make the number corresponding to A with more occurrences shorter, and the number of E and F with less occurrences to be a bit longer, and the rest is in the middle. We calculate the total code length again. The 45 of A is multiplied by 1, the 13 of B is multiplied by 3, and so on. The total is 224,000, which is a lot less. In fact, this is already the optimal solution. As for how variable length encoding comes from, we will introduce it later. Now let's think about a problem. Can we change the number A from 0 to 1? In this way, the length of A does not change, which seems to be no problem. Then we try to decode. For example, this is a string that has been encoded. Then we decode. First of all, if split like this, it is equivalent to A and B. If viewed as a whole, it is the number of E, that is ambiguity in this way. And if A itself is 0, for example, to decode this string, the first 0 must be A and the rest must be B. There is no other possibility. Therefore, no code is the prefix of other codes, which is called prefix code. In fact, it may be more appropriate to call it prefix-free code. In short, it has the same meaning. Variable length encoding requires such a requirement. In order to facilitate decoding, a binary tree is introduced. The rule is, if it is 0, then the left child node. If it is 1, then the right child node. So for A, it is 0. To the left, it's A. Then there is a B character, the first one, and the right subtree. Then there is 0 in the second place, which is left subtree. The last is 1, the right child node. By analogy, a binary tree is formed. However, there is no order here, not a binary search tree, and the same fixed length coded subtree is like this, more well proportioned. As you can see, the variable encoded binary tree on the right is a 4 binary tree. That is, all non-leaf nodes have 2 child nodes. The fixed code on the left is not a 4 binary tree, because a node has only 1 child node. Okay, now we use greedy thinking to build Huffman coding. First, we call the set of all characters an uppercase C. According to the source code of the algorithm, first assign the number of elements in the set C to the variable n, which is 6. Then, all the current characters are added to the minimum priority queue, called Q. That is, in this queue, according to the frequency of each character, always keep the order from smallest to largest. Next, we let I start from 1 and loop through it until n-1. First, assign new node C. Then, in the next sentence, take the minimum value from the priority queue Q. That is the first F as the left child node of Z. And in the next sentence, take the minimum value E from Q as the right child node of the root node Z. Next, Add the frequency of the left and the right choke notes, and the frequency of the root note is 14. Finally, insert C into the Q again, still maintain the order from small to large. So next, the second round of for loop. Allocate a new node C and take the smallest two from the Q, C and B, as its leaf nodes. Finally, the frequency of the root node Z is the sum of C and B, which is 25. Then insert into the QQ. Next, let's speed up a bit. Take out the smallest two to form a new subtree. The new root node obtains the sum of frequency and then inserts it into the QQ. Continue the loop. Take out the two smallest subtrees called Z and put them back into the QQ. Finally, combine the remaining two to form the final binary tree. According to the principle of left and right, for example, if we want to get the code of C, then it is 100. The same is true for other characters to obtain encoding. Alright, this video is over here. We will meet again in the next video.